All right, continuing on with our lessons on space. Last lesson, we looked specifically at some of the basic concepts around the celestial bodies that we would see out in space. Looked at stuff like stars and planets and the definitions behind those, understanding what a galaxy is and the things that we would find inside of a galaxy, and then starting to look at something like, or understanding this thing called the universe, or at least our observable universe. And we sort of tied that all together with our cosmic address to give you a sense as to where we are in the universe. Well, today is all about trying to get a sense as to the distances between those types of celestial bodies, and have us appreciate the kind of scale that we're dealing with here. So let's talk about distance in space. First of all, when it comes to distance, we're used to dealing with like meters, centimeters, and then kilometers. And we know that based on distances, we know that kilometers is a great way for us to measure distances in and around us. Getting from here, London to Toronto, we can measure in kilometers. A flight from here to, say, Hawaii, we can measure that in kilometers as well. But how does that hold up when we start getting outside of Earth? Well, let's take a look at some distances if we were looking at it from kilometers and looking at it from here, let's say, to the moon. So from here, Earth to the moon is about 384,000 kilometers. From Earth to, say, Venus is 43 million kilometers. And from the Earth to the Sun is about 150 million kilometers. These numbers are quite large, and we're just talking about sort of distances within our solar system here, the solar system comprising of our sun and the 8 other planets that orbit around the sun. So we start to understand pretty quickly that kilometers is just too small of a distance or a unit to measure distances in space, in particular just those examples, distances within our own solar system. So we have a different unit that we can use. And we just mentioned that the distance between the sun and the Earth is, roughly speaking, 150 million kilometers. Well, we would take that 150 million kilometers and we would say that that distance is what we would call 1 AU, or 1 astronomical unit. So now all of a sudden, from here to the sun is 1 AU. So if we were to use the astronomical unit, or AU, as our new distance or unit of measure, we would then say that the distance between Earth and Venus is about 0.3 AUs. The distance from Earth and the last planet of our solar system, Neptune, well, that distance can be described as about 29 AU, or 29 astronomical units. So the next closest star to us and our sun is called Proxima Centauri. And that star, which is within the Milky Way galaxy, but that star is about 40 trillion kilometers away. Or we could say about 268,000 astronomical units. So that becomes a bit of a problem. We're just talking about the distance between our sun and the nearest star, Proxima Centauri, and we're already talking about distances of hundreds of thousands of astronomical units. Maybe the AU, or the astronomical unit, is just too small of a unit or distance to measure distances outside of our solar system. Okay, so we go to a different unit, and that involves light. Now, light can travel at a really fast speed. In fact, light can travel about 300,000 kilometers per second. 300,000 kilometers per second. And it's a little bit less than that, but it's pretty fast. Now, at a speed of 300,000 kilometers a second, you might be thinking, how is that going to allow us to measure distance? Isn't that a speed? Well, let's take a look at this. For example, when light leaves our sun, it takes about 8 minutes for that light to hit Earth. 8 minutes. You can see here on this video that this is the replication of what that kind of speed looks like, with light leaving the sun and heading towards Earth. And in fact, if you were to measure the amount of time it takes the light from the sun to get to our last planet in the solar system, Neptune, it would take over 4 hours. Now, if we let light travel for a year, just traveling out through space, how far would it go? In the course of 1 year, light would travel 9.5 trillion kilometers. Trillion, that's like 12 zeros. And that 9.5 trillion kilometers is what we would call the distance of 1 light year. So that is our new unit of measurement when it comes to distance, 1 light year or 9.5 trillion kilometers. Now we're using light years to measure distances away from us. And for example, that would mean that Proxima Centauri is roughly about just over 4 light years away from Earth. So light years becomes a really handy unit to use when we're talking about distances to stars. However, that becomes different when we talk about stars that are really outside of our galaxy called the Milky Way. For example, the nearest galaxy to our Milky Way is the Andromeda Galaxy. And that galaxy, just like the Milky Way, is just made up of a whole bunch of stars and planets and all of that kind of stuff. Looking at the distance between us and Andromeda, our next door neighbor when it comes to the galaxy, that is about 2.5 million light years away from us. 2.5 million light years. Let's talk about how are we able to even measure this in the first place? How can we even determine that something is 1, 2, 50, 100 light years away when we don't have anything that's taking a measuring tape and moving its way out to that object? How do we know that an object is that far away when there is actually no way for us to measure that distance ourselves? Parallax. Now, you are already very familiar with parallax. In fact, it's that phenomenon if you were to look out in front of you and hold an object like your thumb or your hand out in front of you, and you look at it with one eye and then flip to the other eye and look at that same object and flip it back and forth, you would notice that the background behind that object that you're looking at will actually sort of shift and it will move. And if you focus in on the background and you do the same thing, you would notice that instead of the background shifting, your thumb actually does the shifting back and forth, back and forth, back and forth. And that is something that we can use by looking at an object from two perspectives, specifically one eye versus the other eye. And when you start looking at an object and seeing that shift, we can use that shift as a way to measure stuff like angles. And we can use something like triangulation to figure out how far an object is based upon the amount of shift that we're seeing in that object as we look at it from one eye or the other eye. Now the thing is well, when we're looking up at a star, we're not doing that with our eyes. We're doing that with the position of the Earth in relation to the sun. So let's say in January, we'll take a look at a far off distance object, take a look at it with the background in the back, flip around 6 months later to say July, and take a look at that same object again and notice the shift in the background or the shift of the object against that background. That's like us changing eyes and seeing that shift in that object against a stable background. Well, we can measure that and we can determine angles from that, and as a result, using triangles, estimate how far off that object is. That's using parallax. And I've really boiled it down to sort of a quick summary of it. But that is essentially how we can use parallax to help sort of estimate the distances of objects to a certain distance. But the reason why I bring up the use of parallax and how that's used to estimate the distances to far off objects is because that brings us to our next unit of measurement. So we've gone from kilometers, too small, to astronomical units, which are great, but only within our solar system, to now light years, which is great to a certain degree, but maybe there's something that's a little bit longer. And we'll go up to something called the parsec. And parsec is really determined by the use of parallax. And we're not going to get into the details of it, but that's how we derived a parsec. Now, how far is a parsec or 1 parsec? It's roughly about 3.2 to 3.3 light years. But the parsec is from the use of parallax and noticing this pattern between the angles and how far that object is based upon the shift that it has against a stable background. That's it, the parsec. You may have heard the phrase that looking up at the night sky and seeing the stars in the sky is kind of like looking back in time. And I'm hoping you can understand why that's true. We just said that the sun's light that is hitting us right now on Earth is about 8 minutes old, meaning that it took 8 minutes for that light to reach us. So the sun that we're experiencing right now is the sun as it was 8 minutes ago. Looking up at the star Proxima Centauri, the star closest to us here on Earth, we just said that that star is about 4.2 light years away, meaning that the light that we're seeing shining on us, or that we can see in the sky of Proxima Centauri, is about 4.2 years old. So the star that we're actually looking at is the star as it was 4.2 years ago. In fact, when we look up at the sky, all the stars that we see in the sky, the individual stars, are really stars within our own galaxy, the Milky Way. And when we start looking at just how big the Milky Way is, those stars that we see up there, some of that light that we're seeing has taken about 300 years to get to us. That's because some of the stars are about 300 light years away. And if we find one of those stars and we look at it, again, that's the star as it looked like 300 years ago, looking back in time. So when we look up at the night sky, is it possible for us to see any other galaxies besides just our own Milky Way? Yes, you can. And in fact, there's a couple. The Andromeda Galaxy, like we said, is the nearest galaxy to us, and you can see that up in the night sky. The thing is that it's not going to look like a galaxy. It's really going to look like just a point of light. It's going to look very similar to a star, and that's because it is that far away from us. And we said that the Andromeda Galaxy is about 2.5 million light years away from us. That means that if you were to see this point of light and recognize it as being the Andromeda Galaxy, that is the galaxy as it looked 2.5 million years ago. Time travel. Looking back in time. It's awesome. Isn't it? It's awesome. Travel. How are we going to travel across these distances that we've just talked about? Well, our current rocket technology, which is really just a chemical type of rocket, and that includes the Merlin engines that are used to power the SpaceX rocket. Those, when out in orbit, can achieve speeds of about 40,000 kilometers an hour. So, roughly speaking, if we were to use that kind of rocket to get from Earth to Mars, that could take anywhere between 6 and 9 months to get from Earth to Mars. 6 to 9 months. The reason why there's that range is because it depends on where we are in relation to Mars as we orbit the sun. But 6 to 9 months. So you can imagine the challenge that we're faced with if we're trying to get outside of the solar system. You got to understand that if this is a plan for you, that the rocket or the vessel that you're going to be using to get from here to outside of the solar system, you need to think about a vessel that will transport people, understanding that they're going to be traveling for quite a while. And the people that leave Earth on this vessel will not be the same people that get there when they finally arrive at their destination. So if that is something that you're looking at designing or planning on how you're going to get to another planet, you need to consider long-term travel in space. So as a result, there is this need for us to research and find out new types of rocket technology. One, for example, is the nuclear thermal electric propulsion unit, which uses nuclear energy to heat up hydrogen gas, and that gas is basically shot out the nozzle, and that is what propels you forward. Apparently, it can get you speeds that are a lot faster than your typical chemical type rockets, and they would say that you could cut down travel to a place like Mars. Instead of 6 to 9 months, you're looking at 30 to 60 days. So there is still a lot of study and research required when it comes to trying to get around in space. But it's something to consider, whether or not you're traveling within the solar system or outside of the solar system, is how are you going to get there? And consider the amount of travel and the distances that you need to traverse in order to get to your final destination. So that is the end of the lesson. Now, so you can kind of see these topics are going to help you determine what you need to overcome in order to get to your destination. Distance and travel, and understanding, are you going to stay within the solar system, or are you now going to try to get to another star or even a different galaxy? So we're starting to get the wheels turning here, and I'm hoping that you're starting to generate some possibilities as to a pitch that you will come up with as where are we going to go to next now that Earth is no longer inhabitable? Where can humans go? The homework for today is really for you to continue on with that. Like I said last day, there's really only one assignment for this unit. There is a questionnaire I want you to fill out in terms of just letting me know what kinds of ideas you're starting to come up with, you are by no means signing on the dotted line here. You could still change your mind, because as you understand more and more of the stuff, you might think, well, okay, I was going to go there, but after learning this, I think I might change it and go this way instead. That's fine. But take just a few minutes to give me some ideas and to list down any questions that you might have so far, because if we're not going to cover it in class, I want to make sure I at least add it into the lessons, so that way you've got the information to go forward with your project. So that's it. End of the lesson. Continue thinking about your solution to our problem of getting to another planet, and just give me a quick feedback thing on this form that I've attached in Google Classroom.